Hi, welcome to Algebra 2 Common Core. Today in lesson number 3, we're going to solve quadratic equations that have complex solutions. Now to begin with, we won't be able to tell which quadratic equations have complex solutions versus real solutions. But by the end of this unit, we will have a way to distinguish between quadratics with real solutions and complex solutions. So let's stop the video for a minute and fill in the two methods that we have for solving quadratic equations. One that we will be using quite a bit today is the quadratic formula. The second one, completing the square. Please also write down in the box what the quadratic formula is. And when you come back, we'll do exercise number 1 together. So did you write down your quadratic formula? X is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. In exercise number 1, let's use that quadratic formula to solve this quadratic equation. X squared minus 4x plus 29 equals 0. Remember, when we solved quadratics using the quadratic formula, we want to start by identifying the a, the b, and the c. So in this equation, a, which is the coefficient of x squared, is equal to 1. b, which is the coefficient of x, is equal to negative 4. And c, which is my constant, is equal to 29. Go ahead and use these values for a, b, and c in the quadratic formula and simplify, and then come back and we'll talk about our solutions. So I substituted the values a, b, and c into the quadratic formula, and I got 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 29 all over 2. Now simplify what's underneath the radical, so the radicand gave me negative 100. Now we should recognize with our work in imaginary numbers that the square root of negative 100 is really equal to 10i. So I'm going to say x is equal to 4 plus or minus 10i divided by 2. Now when I'm doing the simplification, I need to divide both terms in the numerator by that 2. So that's going to give me a result of 4, not 4. That's going to give me a result of 2 plus or minus 5i. Now remember that this really stands for two answers. One answer, 2 plus 5i. The other answer, 2 minus 5i. Remember that when I've got the same exact real part, but the imaginary part has the opposite sign, these two answers are called complex conjugates. So one way to solve for a quadratic that has complex roots is by using the quadratic formula. Now let's take a look at exercise 2, where we can try an alternate method for solving a quadratic. So this one says, let's solve by completing the square. This will be great practice for us anyway. We haven't done completing the square since when we were practicing for our midterms. So remember that I've got a quadratic, so this one we're going to start with x squared plus 2x. To do the method of completing the square, we want to move that 10 over to the other side of the equation. So let's subtract 10. Do you see that I've left this blank spot here so that I can complete the square with the trinomial? So we're going to take half of this center term. So half of 2 is, of course, giving me 1. And then I square that 1 and I put it right here. I'm going to add 1 to both sides of my equation. So if I've added 1 to the left side, make sure we also add it to the right side. On the left side, this trinomial is now a perfect square trinomial. So let's factor this. It would factor into x plus 1 times x plus 1. But of course, since it's a perfect square trinomial, I can write that as x plus 1 squared. On the right side of the equation, negative 10 plus 1 is giving me negative 9. My next step is to take the square root on both sides of the equation because I'm trying to solve for x. So when I take the square root of something squared, it's just giving me x plus 1. On the right side, the square root of -9, there's another one of those imaginary answers. So this is giving me the positive and negative 3i. I could have also put the positive and negative up here on this line, showing that when I take the square root on the right, I have to remember to take both the plus and minus. Finish it off. To get the x by itself, let's subtract 1 from both sides of the equation. So this is giving me x is equal to -1 plus or minus 3i. Yes, my two solutions are both complex. One solution -1 plus 3i, the other solution -1 minus 3i. Again, we saw that we got complex conjugate solutions. So these two methods, quadratic formula and completing the square, are both going to be useful in solving quadratics even when our roots turn out to be complex roots. So let's take a look at exercise number 3 and try another pair. So let's look at the example on the left side. X squared minus 5x plus 30 equals 7x minus 10. Now this is quadratic because it starts with an x squared, but we have to write it in standard form first. So I'm going to subtract 7x from both sides of the equation, and I'm also going to add 10 to both sides of the equation. So in doing this, I'm getting x squared minus 12x plus 40 equals 0. How about if we do this one by completing the square? So in standard form, I want x squared minus 12x, and I want to figure out what else do I have to add to that to complete the square. In so doing, I want to move the 40 over to the other side of the equation. So completing the square, I'm going to take half of that center term, so half of -12 is -6. Square that, so I get a plus 36. Let's also add 36 right here on the right side. Factoring on the left side, we're always going to use our half number in our factor. So that's going to give us an x minus 6 squared. On the right side, -40 plus 36, -4. Now go ahead and take the square root on both sides. On the side with the number, we'll do the positive and negative square root. So we get x minus 6 is equal to plus or minus 2i. Adding 6 to both sides, my solution would be x is equal to 6 plus or minus 2i. Two solutions, 6 plus 2i, 6 minus 2i. Again, these solutions are complex conjugates. So look over your work and make sure you understand the process of completing the square, and also identify why we ended up with complex roots in that answer. Let's go ahead and try B. Again, I've got a quadratic, but I need to put it in standard form. So let's subtract 10x from both sides of the equation. Let's subtract 4 from both sides of the equation. And I'm getting x squared plus 6x plus 9 equals 0. Oops, I think I subtracted that wrong. So that should actually be x squared plus 6x plus 11 equals 0. Good thing I checked that. Okay, we did completing the square in the last example, so how about if we try a quadratic formula here? So we're going to say a is equal to 1, b is equal to 6, c is equal to 11. So using the quadratic formula, x is equal to the negative of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I get for my solution negative 6 plus or minus. We can either do this on our calculator or in our head. 6 squared is 36. 36 minus 44 is negative 8 all over 2. Now let's see what happens when I simplify this radical. Negative 6 plus or minus. 8's not a perfect square, so I'm going to break 8 down into 4 times 2. The square root of 4 is 2, but there's still another 2 underneath the radical. And because I had a negative under the radical, that tells me I have imaginary solutions, all divided by 2. And when I simplify this, I've got to take all 3 coefficients, all 3 outside numbers, and divide by the same thing. All 3 can be divided by 2, so that's going to give me negative 3 plus or minus radical 2 times I. The denominator, when I divided by 2, would just give me a 1. So my two solutions here, negative 3 plus radical 2i and negative 3 minus radical 2i. And again, make sure that you're not putting the I underneath the square root sign. Either of these problems could have been solved by either method, completing the square or quadratic formula. So we're going to practice some of each tomorrow in class. In exercise number 4, we're looking at the parabola whose equation is y equals x squared minus 6x plus 13. It says, first of all, algebraically find the x-intercepts. Remember that x-intercepts just means that my y-coordinate has to equal 0. So that tells me that I'm going to replace the y with a 0. So 0 is equal to x squared minus 6x plus 13. Now what we'd like to do is solve this algebraically. So we have two options. We can use the quadratic formula, or we can use the method of completing the square. You decide which method you want to use, pause the video, do whichever method you like, and then come back and check with my solutions. I chose to do this problem by the method of completing the square, but we would have gotten exactly the same solution if we had used the quadratic formula. So in my solution, I got x is equal to 3 plus or minus 2i. And again, that's two separate answers, 3 plus 2i and 3 minus 2i. Now remember that the question actually says, let's find the x-intercepts of this parabola. So let's take out our graphing calculator, and what we'd like to do is use the calculator to sketch a graph of the parabola. On the window it says let's go from negative 5 to 10, but I don't think we're going to be able to fit the whole parabola on that grid. You can switch your window on your graphing calculator so that you can see a little bit more. I am going to also set up a table of values. So for my table of values, I think I want to go ahead and use, let's say the numbers from 0 to 6. And again, if you enter this in your graphing calculator, it's going to be obvious to you why we're using 0 to 6. So find your calculator and make the table of values on your calculator. And then go ahead and sketch this parabola and come back and check with mine. I made my table of values using my graphing calculator, and then I plotted these points so that I can see this parabola, y equals x squared minus 6x plus 13. Again, I'd like to go back and focus on the idea of finding x-intercepts for this graph. Do you notice that there's no place where this graph crosses the x-axis? So we can say that this parabola has no x-intercepts. That's going to be a really important concept here. Now when we look at part C, it says from your answers to part A and B, what can be said about parabolas whose zeros are complex with non-zero imaginary parts? So my two solutions were 3 plus 2i and 3 minus 2i. Clearly I see that when I have complex roots, that's going to show me that my parabola does not cross the x-axis, or my parabola has no x-intercepts. Tomorrow we're going to start looking at what determines what our parabola is going to look like. What determines what kind of roots or x-intercepts I have for a quadratic? So give some thought to that tonight, and then our lesson tomorrow will talk about how we determine what kind of parabola we're going to be graphing. Have a great night, and we'll see you soon. Bye-bye.